Yeah, hello again. Just for the record, my name is Chris. I'm a second year PhD student under the supervision of Paul Brennan. Today, we're going to talk about the first part of our project, high resolution radar imaging of pyroclastic density currents. We also call it HRI-DDC. And I'll talk about the trigger system, our first field trip today. And soon, Dr. Amiri will be giving a presentation about the radar part and the test and development of the system soon. And the last field trip that we finished a couple of weeks ago with live on will be presented sometime soon. So today, I will start with what a pyroclastic density current is, because that's a phenomenon that I had no idea before I started my PhD. I'll talk about the project a bit and why do we need to develop automated detection and the detection algorithms in the literature, the device that we prototyped, tests that we applied. I'll talk about the fieldwork that we done in February this year and some challenges, discussions possibly together, and I will share some individual results. So let's start with the volcanic eruption patterns. They can be simply divided into three. The first outcome of a volcanic eruption is the lava fountains that are the lava goes into sky after the eruption, and then they come out to the earth. And these are called lava and tephra fallouts. And the third and the most dangerous part, deadliest part of the volcanic eruption is the pyroclastic density. To give a better insight of it, I'll share a video with you, which is from research 2018. And the video is from the journal Nature. Hope you can hear it. If you can't hear it, you can't hear the sound. Just like drop a text to the chat box.
This is a pyroclastic. It's racing down the side of the volcano. Hot, fast, down. Pyroclastic flows are fast flowing currents of rock, ash, gas produced during volcanic eruptions. They can move at several hundred kilometers an hour. But no one knows exactly how these pyroclastic move. Thousands of kilograms of high volcanic material produce a lot of friction, but they seem to flow like a liquid. So what's really going on? It's difficult to study a pyroclastic flow on an active volcano. So these researchers, they're
I love the last sentence. They say it's extremely dangerous to study pyroclastic density currents on active volcano. And this is what we are doing. Well, first, like a recap of PDCs. They are fast-moving, destructive, and fatal outputs of the volcanic eruptions, and they are like accused to kill more than 90,000 people over the last 400 years. But the thing is, there's not much known about their flow dynamics, as yet there's no instrumental vision of their major parameters, and that's why they are a bit of unpredictable, because there is still no proper modeling provided then. So it is kind of an interdisciplinary research, and that's why for this project we have a collaboration with University of Zahan. They do numerical modeling and photogrammetry of the data that the radar people from UCL provide with our custom-built system. Also, from University of Liverpool, we have another colleague, Sylvia, who is a volcanologist. And in addition to all, the local authority, SUBIME, it's the Institute of Volcanology, Geology, Seismology, all the kind of logies in Guatemala. They kindly offer, provide an engineer with us each time that we do our field trips. And the role of us in this project is obtain the high resolution data by deploying custom built system, which has an automatic trigger function. And the subject volcano for this project is the volcano Santiaguito in Guatemala, as it is quite active volcano. So this is the system overview mainly. We have more than 2 bucks of it, but it's just a quiet version. So we have RX, TX units and an ADC, and mainly 2 dishes to aim to the volcano surface. But the main thing is we can't really run the radar 24/7 as there's no power. We are relying on solar panels, batteries, and the memory is limited with the solid disks that we have. So we don't really want to log all the data continuously. Besides, even if we had a chance to have like an endless power and endless memory, that wouldn't be easy to process data to see which is dummy data and which is the data belong to the Pyroclastic. So that's why we need a trigger system. And we use some geophysical sensing instruments to sense the eruption and to trigger the system. So simply, system has 2 stages. One we call the passive region. During the passive region, it's just the eruption detector acts as a watchdog. And once it senses the eruption, it triggers the rest of the system that are the radar, ADC, computer, and all. And the system logs the data for a user set time, we set to 6 minutes, and then it gets back to the passive region till the next trigger. And the aim of the automatic detection here is we need accurate eruption sensing. We need to be power efficient because the system is on all the time. The system has to be flexible. This is such an important feature of the system because most of the detection parameters are unknown, as they are up to the type of the soil because it affects the speed of wave, and it's also about to the nature of the vibration that the volcano creates. So a lot of unknowns about the parameters. That's why the system has to be flexible, has to set the field mainly. Another thing is the system has to be IoT compatible because first we want to monitor the system while it is in the Guatemala and UK. Second, we need to remove control while we're in the UK. So we need a solid IoT connection as well. How we got these features is of course improving the existing algorithms, developing a new system which serves the purpose that we need. And the possible contributions of such a system is first, it's the remote control and trigger system for such an never done radar before. And the trigger system is quite small. You see it, not bulky. It doesn't consume much power. It is quite easy to deploy compared to the other devices literature. And it does standalone detection. You don't need a base station to do the detection decision. Everything is happening on board, and it's just relying on one earphone. It has pros and cons, but for us, it's just easy to deploy again. It does real-time processing. It doesn't log any data. It doesn't save any data. It gives us quite fast sampling rate, which is around 7 hertz. Considering that the signals that we are dealing with all around below 50 hertz, that's more than enough. And risk mitigation, of course, it does like remote sensing and does the automated detection and security risk. And in terms of the detection methods, I want to talk about a kind although we're not going to use it. It's just, I think by now it's 65,000 times cited. That's a huge paper. I don't know if you ever heard about it, but it's actually a statistical model. What I understood using an error rate, between like a set of data and your algorithm, and in the literature they make use of by using same eruption data, and they compare it with the sense data, and if the error rate is smaller than a threshold that user sets, it says yeah, it's likely to be an eruption. But as it sounds, it requires a lot of computing power. So that's why the company uses it. And our initial method was the amplitude, also RMS threshold trigger. We combine it with FFT. But the main issue with it is simply it's a threshold. If the vibration is higher than the threshold that is set, the system gets triggered. But you become a bit too vulnerable to the stimulus, like spike by activity. So if someone just taps on, or I don't know, your dish because of the wind gets, I don't know, any movement, the system gets triggered. So that was the initial aim, but then we switched to the short time average over long time average method, which we call STA and LTA. What it does simply, you have two averaging filters. One has long constant, the other has short constant. The long time constant one gives you a threshold, like a noise level. And the short time constant one is the one that you compare with the time, but as it's not like as you have a short time, say, I don't know, a couple of seconds to average the signal amplitude, saves you get triggered by the stimuli sort of waves. I'll give some more detail about it later, but we need to talk about the device that we are doing the digital filtering first. We're using an Arduino, Nano 33 VLE, and we are running some code on it. It has a lot of IIR filters, and to test it, we run the code just for one IIR filter with 50 Hz cutoff frequency, and as you see, at cutoff, it is giving almost minus 3 dB, which is nearly perfect, but the disparity increases when it goes to the higher frequencies. For 500 Hz, it's almost minus 18, which is not perfect, but it serves the purpose. And for the trigger, we initially aimed to do the system to get triggered by both seismic signal, which we acquired through a geophone, and the sound signal from a microphone. But then we realized that it's not that easy to have a microphone for this low frequency. I mean, it's expensive and requires some other application stages and a lot of stuff. So that's why we switched to the geophone only. What we simply do after an amplifying stage, which is an op-amp circuit, has more than one amplifying stages, overall more than 60 dB gain. And once the signal is sensed by Arduino, the first thing we do is a high-pass filter that allows us to get rid of the DC offset, because we have 1.65 volts DC offset as we are using single variable amp. And then the low pass filter is required because, as I said, the seismic signal, it's the nature of the volcano. Like, since they are relatively big compared to the Earth surface, the movements that tend to be slow. So the frequencies emitted by the volcanic eruptions are mostly around like below 50 Hz. And then you rectify the signal. And here, here's our STLK block. As you see, we have two filters, basically. And the long time constant filter gives us the average amplitude of the signal for, say, 40 seconds. And the STA filter gives the average for, say, 2 seconds. And once the short time average is higher than the long time average multiplied by a user set threshold, which is K here, system gets simply triggered. Mainly, we have two Arduinos in the system. One is the Arduino Nano 33 BLE, which does the sensing, which has the detection algorithm running on it, and the user SCDN keypad interface, and this is the one that makes the radar, power supply, and the computer on. And just for the IoT connection, we have another Arduino that establishes the GSM connection as like a communication. The other Arduino. The reason that we are using two Arduinos, I'm glad that we decided to use two Arduinos. If the connection drops down at this MPR side, we want the system to log the data, even its local data. So even if we can't reach the data, we want to make sure that the system is logging the data. And this is how we ended up. I'll give more details about it. But that was a good idea to have two different Arduinos for doing two different purposes. Testing for the IoT triggering and monitoring testing, that was easy. I will show another short video. This is our room in Guatemala, the hotel room that we did final tests. So I will show the system overview. This is the box, and that light indicates that the Arduino is connected to IoT. This is solar power MPPT, and it shows 12.913 volts. And for more accurate voltage, here we have 12.9 again. And this is the IoT screen. It doesn't have any physical connection. It's through GSM connection. It shows 12.9. I'm triggering the system now. There we go. System's off, as you can see here. And the previous system, the initial system we had, was based on a Windows installed computer. So we were able to make the system up and reach it from here, from the UK. But the algorithm testing, it's not as easy as the IoT testing, because I mean there's not much options to vibrate the geocode with that low frequencies. Like the vibration table able to work below 50 Hz would be, I don't know, candidate test, but we weren't able to acquire the CL. So what I did is, if you remember, I mentioned that we have volcanologists. So I asked him to provide some, let's say, data from the same volcano corresponding to the volcanic eruptions. And I used a MIDAC as an arbitrary function. And I fed the system, fed the board directly with the eruption data. And it did get triggered. However, it doesn't say much about the force. It is obviously. It does prove that the system gets triggered with the proper eruption data. However, I mean, there's no way to talk about the force triggers. And that's the reason that the system mostly had to prove itself to build. And the first field trip, this is first trip from London to Madrid and Madrid to Guatemala City, and another city, small city called Quetzaltenango. And as you see, we made a huge U-turn to somewhere quite close to the Santiago. The reason, although the volcano is quite close to the city, there's no way to go there. So we made almost 100 kilometers. Big U-turn with SUV cars. And on the left-hand side, this is our pack here in London, Emmons Place. And the van that you can see in the middle, with the all the stuff. And at the right-hand side, us arrived to go to the airport. I know, like, the packaging is not the same with the initial combination, but it's another journey. I'll just ask you, look at it. Oh, luckily, nothing was broken, nothing was lost. But we are quite lucky about transportation because like, we checked all of these as luggage. So no special kind of transportation with them. And the first day, is the day we met the Insume people, Guatemalan institution, and we introduced our system to them. This is the garden, Insume Guatemala. And then we started to do field work. This is the assembly part. We assembled by both the radar and the seismic system. The picture here, you can see the CDN keypad, the receive box. This is the user interface of the detector. And in terms of the seismic data logging, I need to mention that we have a device there, which is a data cube here, and two different geophones, the yellow one and the red one. The yellow one is only for the data log, so the data cube that you can see at the picture far right hand side. This is the data cube that's at military grade device, which is nice. You got it from, again, we got it from what quality. It just logs the data, it does nothing else, it just logs the data, saves the data, all the seismic data, all the seismic events happening in the field. And the red one, the red tiny geophone here, that one, it is, as you see, it goes into the box, and this is just for the detector. So we have two geophones, simply. One is to log the seismic data, and the other is to do the real-time processing, trigger the system. And tuning, for the right-hand side again, in the middle, we do some antenna tuning and the right-hand side, we're doing some more tuning with the detector. I will give more details about it because it wasn't easy to do tuning while people are walking around, because every moving thing in the field is a source of vibration. So that was a challenge, and I will give more details. But as you can see, I stressed a lot about the flexibility of the system. I don't know if the online people that you can read the screen, but all of the detection parameters that we can set in the field easily with a CDN keypad interface. And this is really how we made the system get triggered for a time. And like one of the most amazing parts of the trip is we serve a lot of eruption with naked eyes. The last trip we began with live on, the weather wasn't this good to see all the eruptions, but the February trip was perfect. So at the left-hand side, you can see the eruption has just started. And right-hand side, I mean, for us, that was a huge eruption. You can see the flow here. That was a big eruption for us, but for the local people, it's just so normal. We were amazed, like, look at that, look at the flow. They're like, just a normal eruption. I mean, they say during this season, rain season, they got bigger and bigger. But yeah, this is one of the eruptions. We've seen tens of them, probably. This is one of the eruptions that we've seen at Negro. And yeah, that was one of the best points. And challenges on people all around. it's not easy to know you go tomorrow. But yeah, main challenges that I mentioned was tuning. So after some point, I had to ask these gentlemen to go far away during the night, made some fine tuning while they were sipping their lagers at the landlord's mansion. And the internet connection for dinner dropped down while we were in the field. And we used like simple plastic pipe as a pole. We had to use a plastic pipe because of the risk of lightning. And IoT time drift, we had a huge time drift. That wasn't an issue here in the UK. Yes, and that wasn't an issue even in Guatemala, like in the city. But once we start to observe the connection keep going down, the time drift between the computer and the time that we see on the IoT screen, like started to have a huge disparity. And we sorted out in an RPC model for the next system. But that was another challenge that we need to overcome. The gain adjustment, as I said, like we have over 60 dB gain through more than one point. I was using simple trim poles that we all use from our board, like the bones ones that we simply adjust and flat screwdrivers. That was fine again here in the UK. But I did feel like even twisting them with the screwdriver and probing them, estimating or calculating the gain became huge pain. So for the next system, I use binary coded SIP switches. I use 4-bit as 16 binary coded decimals. No. Binary coded. So anyway, so like it has 16 positions, say, and if all 4 bits are connected to like valve line, say, valve choosing resistance, it provides you the resistance from like a high value to a low value. So I place it to the feedback part. Once you set it, you can visually see the position of the flip switch and the resistance corresponding to that. So it's easy to set the gain there. And the router, as I said, connections keep dropping down. We just realized that we have enough power to leave the router doing always on, because we have 600 watts solar panels there, 400 amps of batteries, and we just realized that it's funny enough to leave the router always on. And considering that we had a lot of issues with the Arduino's connection keep moving down, and if we have the router on, for the next is to switch the GSM connected Arduino to the Wi-Fi. And here are some results of the detection algorithm. Here you can see the signal is the signal logged by the data cube that I just showed. And this is a random data that I picked, it's 11th February. As you can see, the system, that's not mixed event, but a system is being triggered quite well during the course of the deployment. And I'll show another date, which is 90, where we again, oh, sorry. Again, there are some missed events, but luckily, there's almost no false alarms. So it can be discussed further, because I actually haven't processed all the data certain reason. But in a way, it's quite satisfying that we got correct trigger at correct time. With that low cost, cheap delivery price. And I mean, as I said, I'm happy to discuss the possible reasons altogether and provide maybe detection rate algorithm for it. Because I know yes, which is PhD student, is also working false detection rate because I think that's a radar system. So it would be nice to be either. But overall, the initial performance of the tech is actually quite satisfying for us. And the data that we got through radar is being processed. Still, as I said, we're quite happy with what we've got. That's the end of my talk today. This is the end of the field work that is together. And as I said, usually part 2 of the seminar is going to be given by Emin soon. But third part, which is the field trip that we did a couple of days ago, a couple of weeks ago, will be given by me sometime after that we finish processing the data that we got. Thanks for listening. That's it. Really?